Okay, here's some quick, just kind of review notes to remember when we're graphing rational expressions, which we do mostly in sum review number 7. Remember for rational equations with polynomials in the numerator and denominator, we've got the rules that you hopefully learned in pre-calculus. So we have a polynomial in the numerator, polynomial in the denominator. We just look at the degrees of the highest degree term, or I'm sorry, the exponents of the highest degree term. And if the degree of the numerator is smaller than the degree of the denominator, we have a horizontal asymptote y equals 0. If the degrees, and these are just the highest terms, so the highest degree terms are 3. Well, here it was 2, here it was 3, here it's 3 and 3. If the degrees are the same of the highest degree terms, then you have a horizontal asymptote, which is just equal to the ratio of the coefficients of the highest degree terms. So in this case, it would just be y equals 5 over 3, 5/3. That's a horizontal asymptote. It's a constant. And then if the degree of the top is greater than the degree of the bottom, then there is no horizontal asymptote. Okay? But if the degree of the top is exactly 1 greater than the degree of the bottom, we have what we call a slant asymptote. Okay? Now normally the asymptotes will be anything, the horizontal asymptotes are determined by these, excuse me. Now the slant asymptotes you can find by dividing the denominator into the numerator, which I did over here, and just omit the remainder and just said y equal to what you have on top without the remainder. So y equals 3x plus 8 in this case would be, just by dividing the bottom and the top, this would be the slant asymptote. Goes through 8 and has a slope of 3. Now you can try to graph this, but it's a little bit, you have to play around with your scales because it happens quite a bit up or below the axis, all right? Okay, so that's kind of an overview of some of your rules. So let's get at one of these problems. Let's take a look at number 1. And I wrote it out over here for you. Put it down here. And I got some graph paper, and some of this graph paper is on the site, or will be on the site. Okay, and this is the function. Okay, f of x equals 2x all over x squared minus 4, so I factored it. And we always want to try to look for zeros, so we can look for zeros over here. And when x is 0, I've got 0 over negative 4, which is 0, so I got 0, 0. So those are going to be my intercepts. So I know I have that 0.00 on there. Okay, that's 1 point. And then if I look at this, the degree of the top is smaller than the degree of the bottom. So what does that tell me? That tells me I have a horizontal asymptote of y equals 0. Because the degree of the top is smaller than the degree of the bottom. Okay, that's the degree of the highest degree term. So I can mark that in. I can use a green line for that. That's my horizontal asymptote, so that's y equals 0, which is the x-axis. Okay, you can see that, okay? Probably not very good. That's my horizontal asymptote. And then I don't have anything that's going to divide out, so I've got 2 vertical asymptotes. That's anything that makes the denominator 0. So that's going to be my vertical asymptotes. Okay, it's going to be x equals -2 and x equals 2. So I can put those in. We just want to sketch these and get an idea. We don't have to use a lot of points. You sometimes can. And if we substitute minus x or negative x, the bottom will stay the same, and this will have a negative x. I could put that out in front, so it looks like it's going to be a negative. It looks like it's going to be an odd function. In other words, it looks like f of negative x will equal negative f of x. In other words, if I put a negative x in here, that's going to stay the same. If I put a negative x in there, that's going to be negative 2x. I can put the negative in front, so that would be negative times the whole thing. So it looks like it's going to be an odd function. That means it's going to be symmetrical to the origin. Okay, now it could go a lot of ways, so we don't know what's happening. We don't know it's asymptotic. So let's see what happens around the asymptotes. Now, you can try points in here, but this is another method that we're going to use more in calculus. So let's see what happens as x approaches negative 2. All right. Let's say as x approaches negative 2, so this is negative 2 over here, and we can approach it from either the left or the right, the positive or the negative direction, so this would be approaching from the negative direction. Okay? Now let's see what's going to happen with our function. So if we're right at negative 2, we have 2 times 2, that's no problem. And then if we're at negative 2, we've got x minus 2, and that'd be a problem because, I'm sorry, x plus 2. That'd be a problem because if I put negative 2 in here, negative 2 plus 2 is 0, so that's where I'm going to have a problem. And over here, when x is negative 2 and negative 2, I could substitute those in, that's going to be negative 4. So these won't be the problem points. The problem point here is going to be at exactly negative 2. So I just have to worry about that. What's happening over here? Because this would be the same thing as just 4 over negative 4, just negative 1, all over x plus 2. All right, because I can actually put values in. I can't put a negative 2 in here because I'd have 0. But if I put, negative 2, that's positive. So I've got 1 over x plus 2. So this is what the function is going to behave like right around this, so I have to be careful over here and take a look at this. So what's going to happen as x approaches negative 2 from the left and gets really, really, really close? We call this a very small approach. And this is going to be 1 over, and let's say I'm approaching negative 2 from the left, so I have a number that's going to be a little bit more negative than negative 2. Let's say negative 2.0001. So I'm just to the left of negative 2. Plus 2. And what I can see is if I calculate this out, this is going to be 1 over a negative, because it's a little bit bigger than this, negative, and then if I take the difference here, I just get 0.0001. So if I get 1 over a very small negative number, it means like I'm going to have a very large number, because this is 1 divided by a very, very small number, which would give me a very, very large number, but it's negative. So it looks like I'm going to have negative infinity. So I can kind of say, well, since I'm asymptotic and I'm going to go down towards negative infinity, my curve should look something like this. Now I can try some checkpoints if I want, but to see about what it is at negative 3, but I know it looks something like this. Okay, now let's see what's going to happen as it approaches negative 2 from the right. Okay, let's see over here as x approaches negative 2 from the right. So again, everything else would be the same, so I've got the same situation, so I can save a little bit of time. So I got 1 over x plus 2. So that's going to be 1 over, and then I'm approaching negative 2 from the right, so I might have negative 1.9999. I'm going to get really close, plus 2. And then if I take that difference, it looks like I'm going to have about 1 over. And then if I subtract all these 0.999s from the 2, looks like I'm going to have 0.000001. And that's going to be a very, very large number. It's going to be positive. So it looks like I'm going to be approaching positive infinity. So I can be something like this. Okay. Now what's going to happen over here? Well, we know that since it's odd, it's symmetrical to the origin. So we no problem here. This is not going to go back up because that won't be symmetrical to the origin, so we could just bring it down like this. And then this is going to be opposite here, symmetrical to the origin. So that's going to help us. That's going to save me a lot of work here. I won't have to worry about those other asymptotes because I use my symmetries, and that's what we've got. Now let's take a look at it, and you can always check it with your calculator. So I put this in the calculator already to save some time. And I use an 8x8 window. So there's your function over there. Oh, I see if we can see it there. There we go. All right, put that down. You need to put parentheses around the top and the bottom, otherwise sometimes it'll foul the order of operation. So that's what we started with in its original form. And if I go to look at the graph, there's the graph. So same thing. So it wasn't too bad as long as we used the odd function. That saved us a lot of time because we only had to graph half the function and then everything else was symmetrical. And we had our point of interest, our x and y intercepts, which are the same, 0, 0. Okay. So if that makes sense, like I said, you could always, oops, check that, so that's what you've got, okay?